Okay, welcome back. So one announcement is that we extended the deadline for the system goals homework until Sunday night, just to give you a little bit more time. I don't think, actually the homework is not that hard, I think, but it's the first homework which requires you to really understand what x86 is. That system, it's a little harder, I get it. And so our last homework, which we'll assign today or tomorrow, or maybe even like on Monday, just to make sure that there is no overlap, will be about the file system. So just pay attention. So today our goal is to get to that part in the x86 file system, which is essential for the homework. Okay, so let's quickly recap what we were doing last time. So we are talking about file systems, and we're kind of doing the bottom-up approach. So I explained how the buffer cache works. So it's essentially a simple cache of blocks in memory. x86 implements it in a very kind of simplistic way. So it's just a linear scan through the array of buffers, which it reads from disk. And the next layer above the buffer cache is this layer, journaling layer or logging layer. And at a high level, the idea is to prevent file system from getting into some inconsistent state where like you have, because you may have pointers or some semantic dependencies, like meaning a bit of set and a bitmap saying that this specific block in a file system on disk is already allocated, right? But if the file system is not using this block, then you essentially in some state which you don't want to be in because you're kind of leaking block space. And so the journaling is a technique in which if you have several blocks which you want to combine in a transaction, and today we'll get to a concrete example of that, how these transactions are implemented, instead of writing them directly into the data area of the disk here, you like instead of just writing them, like for example, here, and maybe here, you first write them into this journaling area, logging, and essentially say, look, I remember that this block, like you maintain the metadata about where those blocks have to go. So essentially you remember here in the header of this logging area header, you remember that, okay, so this block, a final destination is here, but for now you just write it in the first block of the logging area. Then you write the second block in the second block of the logging area. Then you write the third one in the third block of the logging area. And then you finally, you write this block saying that, okay, by the way, I remember that I have 3 pending blocks. And after you roll this 3 here, your transaction is committed. So meaning that if you suddenly lose power, the moment you reboot, the logic of a file system will inspect the journaling area and we'll see that there are 3 blocks and they have to go into the blocks maybe 55, 61, and 88. So this is recorded here. So you say, look, it has to go into 65. The second has to go into 61, and the third one has to go into 88, right? And the actual data for this block is already saved in the journaling area. And you just like kind of do this. You make sure, I mean, maybe I forgot exactly if I drawing the lines in the right order, but essentially you install these rights, right? So what it gives you is that no matter where you fail, if you fail halfway through writing this transaction, then it's gone because you never rolled this 3. If this number will still be 0, so after reboot, you see that, okay, journaling area is empty, so I don't have to recover. I don't have to, there is nothing to recover. But if you fail here, but before you roll this 3, then again, you lost the entire transaction. But the moment you roll this 3 to disk, so you committed the transaction into this block, you have all the data for recovery is there. And so after reboot, you will just be able to inspect this block, find 3, and install these blocks into the data area. So this is just an overview of what we were discussing last time. And now let's just quickly see how this can be implemented. Any questions about it? So that's a great question. So intuitively, you, like even in this drawing, you may say, okay, hold on, can you just make a transaction bigger than 3 blocks? And in x6, the size of the transaction is fixed, which is a practical design choice to, again, to simplify the code. x6 says there is a formula, and they compute this formula. The ironic fact is that they actually had a bug in this formula a couple of years ago, let's say like 5 years ago. And so they had to fix it. There was a case in which they could overcommit, allowing more transactions concurrently and then potentially running out of space. Right now, I think the formula is correct, but it's not ideal. In a real file system, you might make a different design choice and make sure that the journaling area either grows infinitely or make, again, transactions practically large. The real question here is, what are you going to do with large file writes? Because you say, look, what if I'm really like writing, I don't know, megabytes here, like 4 megabytes. So which means that there is like hundreds of those blocks, right? And as we see later, and it's a great question. So as we see later, what the file system is doing, it splits those writes into multiple transactions, making sure that it's still atomic. But I mean, and again, it's a good question, because at some point the write itself is not a transaction anymore, because you may persist only half of this write, or like a third of this write, right? Because it's split into multiple block level transactions, but really the entire file transaction is not really a transaction, because you can lose parts of it. And again, it's kind of important to understand it, especially if you build something like databases or distributed systems, and maybe you will end up doing some kind of your own transactional logic on top of it. And at this point, you run into this conceptual problem. You say, look, guys, you provide me some transactions, but I don't really like them, like, because I can do faster, bigger, better. And then at some point, operating systems allow direct access to disk as well, to just make sure that people who build databases can build their own transactions. So that's a tricky business in real systems, but in x6, everything is a little simplified. Answers, right? Okay, good. Any other questions? Okay, let's take a look at how x6 builds it. Okay, just to make sure that my goal was to make sure that you guys are reading the source code, or at least well prepared to read it. So let's take a look at how this is actually implemented. So a typical use of this transactional engine is the following. So we have these operations, right? So we say, look, we start every transaction with a begin op. Not an ideal name, I would say. Begin transaction would be a better thing, but maybe they didn't want to overload the term transaction. Then you do a bunch of, like, you access blocks, and you use still the same bread function to get the block from a buffer cache. You update the data of the specific block by like copying something into the data area. But instead of doing block write, use the special function log write. And this is the one which, instead of writing into the data area, will make sure that the block first goes into the logging area. And not quite like that even. In fact, this end op will make sure that this is ensured. But essentially, the logic of this operation is this, right? And I will explain each of them. So the way it works is the following. So the log is maintained in memory as just an array, right? So we have a data structure, which is log, right? And at a high level, it has like logic to implement synchronization, stuff like that. So we'll discuss synchronization, some flags, stuff like that. But the core of it is this log header. And the log header, the simple data structure, is just an array of integers, meaning that, and a size. It remembers, so essentially it's an array saying that, okay, this is the log header. So here's the size n, and just those are the blocks which you have to write. And essentially, every time you do this function log write, instead of writing anything to disk, it just says, okay, I'll just remember the number. in our example, it was like number 65, for example. You say, look, I have to later on write block 65 to disk, and then block maybe, I don't know, I forgot what it was, 67 or 85, something like that, right? And then you update this number to 3. And that's enough. So everything is in memory. So nothing hit disk yet, right? So you just remember that this is the transaction, which will be going to disk. All these blocks like 65, 85, 67, they are sitting in a buffer cache. And since we did the B read for those blocks, they are left here in a busy state. We didn't release them, right? So they're somewhere in a cache. They don't have to be consecutive, right? But we remember the number. We remember that this one cache is like 65 is cached somewhere, 85 is cached somewhere, and 67 is cached somewhere in a buffer cache, right? B cache, right? So this is the entire thing which you did. So this, nothing really hit the disk before you started committing, right? Everything is just remembered in memory, right? And at this point, you say, look, sure. So it's like, let's take a look at how big an op does. Like, that's the logic which I just explaining. So what it does first, it just, as you said, it makes sure that there's enough space to even like start a transaction, right? So it has a logic of saying that I will not commit the concurrent transactions. So if something is already committing, I will just go to sleep and we'll be waiting on it and we'll be woken up later. However, if nothing is committing, I will make sure that this is the formula which had a bug. So essentially, I will make a reservation that I am about to start a new transaction. So, and the way it's like calculated, it's just an upper bound on the size of the transaction. And so essentially, no more than a certain number of pending transactions are allowed in x86. If there is no space, again, you go ahead and sleep, and later you come back when you're woken up. However, if everything is right, you say, look, I'm incrementing this number, another outstanding transaction, you release, and this log write function, which I was just explaining, literally, when you write a buffer, say, look, we will first check whether this block was written before, because maybe you are writing the same block multiple times and you don't know ahead of time. And so you implement this logic of log absorption instead of like you technically can write it twice, but it's probably just wasteful, right? So because it will duplicate the commit when you install the transaction to the data area, you'll just waste your time. And essentially here you say, look, if this block is already in the log, then just fine, just forget about it. Just everything is fine. You break, you don't have to edit. If, however, it's not there, what you do, you say, look, I got to the end of this log and I adding a new number. So simply remember the block number, which I will have to write later, right? And you mark this block as dirty, meaning that the x86 will not evict it without flashing it to disk. So again, like there is like a lot of corner cases, and I don't want to like go into the details, but if you really carefully read the code, to be honest, like convincing yourself that everything is correct is kind of hardish. But and there might be bugs, but again, at the first like iteration, it looks correct. Like bugs in how the logic of this dirty flags and everything is managed. But so, and again, bugs are rare. So people tried hard to get this code right, but there were bugs in this implementation. So the only way to get it right is actually like, I would say, write a formal proof about it. So which is kind of possible these days. But anyway, so we remember this log write, right? So we essentially didn't do anything. We just remembered it in memory, in the log header, right? And then everything happens here, like all the write operations happen when you try to commit the transaction, right? And so if you lose power before your memory is gone, you reboot, nothing has happened because nothing rolled the disk yet, right? And this end op is a kind of funny function. So again, here it says, okay, I will decrement the number of outstanding transactions. And this is a little bit of a trickery here. So it starts committing only when the outstanding drops to 0. Right. And again, like there are multiple design choices possible, and they did it this way. And at this point, they say, look, we'll start committing. So essentially, we set a flag that we are committing and move on to to essentially the commit logic. And the commit logic is in this commit function, which does the following. So at a high level, what it will do, it will first write all the pending writes into the logging area on disk. Then it write this header, meaning, remember in my example, I was using number 3. It hits the disk. At this point, the transaction is committed. Then it will copy the transactions from the logging area into the data area on disk. Then we'll update this number 3 to 0 and write it again in a header saying, okay, at this point, the transaction is done. And if we reboot, we don't have to recover anything. So let's take a look at how it's implemented again. So this write log, essentially, not surprising. So at like what we have right now, we have a log in memory, which remembers which blocks have to be written to the journaling area on disk. And so what we do here is we have 2 blocks. One is 2, that's a block in a logging area on disk, and one is from. And this from is just a block from which we are reading and writing to disk, right? So essentially, the from block is remembered in memory, right? So this is an array of the log, which I was explaining. So it sits in memory, just integers pointing to the numbers, block numbers. And so essentially we pass them again to be read. So we read them again from a buffer cache, which is a little exotic, because you say, but I already had it. So why not to have a pointer, like from here, have a pointer directly to the block, right? Probably a better design choice. They haven't done it. So, but they say, maybe there is a corner case where you have to reread it again, but I don't see it right away. So essentially, now you have pointers to 2 blocks. So the 2 block, essentially, if this is your logging area on disk, so this represents the 2, and somewhere where we're writing this block, this is the from, right? But essentially, we never rolled the from yet. So what we're doing, we're reading from the from. So we did the 2 reads, and we're copying the data from the from buffer to the to buffer in memory. And then we're just writing the 2. So this gets written on disk, right, in a logging area. And then we release both of them. So this one never got written. We played with this block, but we never wrote it, right? But essentially, like, it's the same API which we were discussing before. So this is the release. So everything is released now. Sure, we wrote the log, and the way we write it, so we just like do a for loop across the log header, across the log in memory, going one by one, like details read, copy data, write everything and release. At this point, we say, look, we have to commit transaction to disk. So essentially, at this point, we will write the header of the log into the logging area on disk. And so what happens here is that it's just one block. So what you do here, you know where the logging area starts on disk, and this is the variable which you maintain. So essentially, in a file system, again, if this is your entire logging area is here, your header sits at the very beginning, right? And so you just read it. This is the start pointer. And you read it. You say, look, let's do a typecast to a log header, because you really, like, if this is a 512 bytes block, you're really just writing a couple of bytes, which is size of this log header. And essentially what you're doing, this is the log in memory, right? So remember this array of integers, say, which says, okay, you have to write block 65, 67, 85, whatever. And you essentially write them here one by one. So essentially you copy them into this array one by one, and you just do one single write at this point into this block on disk and release it, right? At this point, the transaction is committed, meaning that if you lose power, you come back, and I don't show this logic, but the file system before even like allowing any other operations will look into this log on disk and essentially says, okay, look, I have 3 pending blocks here, and they have to go into like the blocks itself. The data for these blocks sits in a logging area, and they are numbers 65, 67, 85. So you have to copy them here. And maybe you are halfway through copying them, as we see, and you lose power, and then you we'll come back and copy them again, right? Let me stop here for a second. Any questions about how it works? Again, so you copy things, right? Maybe it's too low level, but let's come back to it in a second. Sure. So one more explanation. So you read the log header block from disk. You essentially say, I will use it, I will treat it as an array. So right now it's cached in memory because all the writes first go to the buffer cache, right? So that's why you did just typecast and you do just this operation in memory. So you just like, this is a pointer, HB, like this is cached in a buffer cache. This is the pointer into this, like physically speaking, like you get the point. So this is, if this is the B cache, this is the buffer which represent this block. This is 512 bytes, which will represent this specific block, which is, if this is your disk area, this is your logging area. And this is the start. You cache this block right here, right? And you just simply say, I have a HB pointer pointing to this memory, right? And now in this tiny loop, you're just updating this data in memory. First, everything is in memory. And only when you do the B write, this block, since it's not like it, we use directly B write API, gets copied into this area on disk, right? Okay, so, and now, since we have all the information about the transaction on disk, we install the transaction by essentially copying data from the logging area into the disk. And again, we just simply run a loop. And what we're doing here, we still so what we're doing here is that we say, look, we still have two blocks. One is the block from the logging area, and one is the block from the data area, right? We read them both, right? And what we have here is that we still use the log in memory to make sure that we have the numbers where they have to go. We read them too. We simply copy data in memory from the logging block to the data block, and then we write them back to disk. So essentially, I mean, we write only, of course, the data block, right? And then we release them both. And that actually moves the data from the logging area into the journaling area, right? And we run a loop, so it's conceptually very simple. At this point, we installed all the transactions, and what we have to do at this point is just remember that the transaction is empty. So what we do here, we simply update the log header with 0. Essentially, when we enter this function, this log header was not 0, it's all in memory. And then we use the same write head function again. So we used it here to first write a non-empty log to disk logging area, and this is we're just updating the empty. So remember, in my example, this one wrote 3, and this one writes this specific 0 number, right? And so essentially, at this point, we write head again, and this logging area, despite the fact that it like, if this is again your logging area of disk, it has a tiny header here and a bunch of other data blocks. And these data blocks we just like wrote into the data area. We don't do anything with these data blocks. We just forget about them by updating the size of this log to 0. And at this point, the transaction is coming. The transaction is fully erased from the logging area. So the question which I wanted to ask on poll everywhere is, in this function, which line is the transaction? Meaning, after which line, if we lose power and we're coming back, rebooting the system, we will have the data. Like we're not going to lose the data. So let me quickly start all everywhere. Activities. Okay, I enabled it. Let me see what's going on here, and I'll present in a second. Let's wait for a second for people to decide. This is what I have on poll everywhere. Let me go back to the lines. So everyone is ready. So who can justify the answer? Lots of monotone dialogue, monologue probably from me, but now finally someone has to engage. Okay, so let's split the screen roughly so we can see both. So who thinks it's okay? 4704. We're writing the log, so not many people think it this way. 4705. Wow. Somehow people are converging to the right answer. So which one is the right one? So right now everyone believes 4705. So why is it 4705?
Because that's the command where the information actually gets written to the disk, so to the memory.
So which information? Let's be more specific. What is written? What is written? No one remembers. Header, yeah. And what is in this header? Correct. So let me explain one more time. So how do we do this? Start from the current slide. Just again, just to make sure that we can come back to it 5 years later or to some other file system and do the same kind of thing. So if this is your disk area, this is your logging area, and this is your, let's say, data area. What we did here is that we have a log in memory, this log variable, right? It has, let's say, in a header, it has number 3 saying that, okay, I remember that I have to process 3 blocks, 65, 67, 85, for example, right? Agree? What we did here, write log. We said, okay, I'll take the block 65 from the buffer cache. We also have the buffer cache data structure, bcache. We figure out that 65 is cached somewhere here, and we write this function, write log. This function rolled this 65 into this logging area. So it's actual data of this 65. Then it goes and writes 67 and writes 85 here, right? And this function, which is like line 4705, it's not just writes the number 3, like it does write the number 3, but it also writes into this header area. It writes specifically, it kind of writes all of this information. It says, okay, like 3, 65, 67, and 85 have to be written to disk. And the moment you wrote it, the moment it hits the disk, then your transaction is committed, right? So it's not really committed in terms of committed, but you're not going to lose it, right? So even if you lose power right after that, you'll come back and it will be there. Make sense? Because after that, what you do this install transaction. Install transaction just blindly copies, like it uses this data from this log header and it writes it into the data area one by one, right? And then it simply says, okay, forget about it. I will now have a log which has 0, and I will write it again. And at this point, this flips to 0, right? Make sense? So, but the moment you pass line 47, stuff is on disk. There is a tiny little simplification here. So in reality, the things may not hit the disk. So if you're really careful with databases or something like that, you really have to make sure that you somehow get a confirmation from disk that the data is actually written. And so because disks have internal caches, they may not flash immediately. So there is like, it gets a little bit harder in practice, but it's almost there. Any questions about journaling? At this point, I believe we all kind of understand it. I close the poll. People are still deciding. Deactivate. All good? Let me also make sure that I know what I'm sharing. Okay. Question. Yeah, that's a good question. So what you're saying is maybe I'm asking this question in a slightly lousy manner because I'm not clear on the terms, and I honestly don't want to be clear on the terms. So probably you should go talk to someone from the database community and yeah, it's more of a philosophical distinction when you believe that something is committed. So in my world, the moment you persisted, okay, probably a better word here is persisted, meaning that it's saved, so you're not going to lose this transaction. And then the full commit probably happens in line 4710 when you like said, okay, the log is empty, transactions are done, right? But yeah, persisted probably is a better term. Any other questions? So we got this trick. Journaling is aggressively used all over the place in most file systems because it's so simple. There are ways to make sure that, I mean, the biggest disadvantage is that you write the disk twice, right? So, and like, that's it. So if you're willing to accept it, you will be fine. The idea which makes it practical, the main observation is that writes are kind of they are not on a critical path. You can kind of write once into the journaling area and move on. And if your journaling area large enough, you can catch up with installing transactions later, meaning that, if you're aggressively writing something to disk, so maybe you have a burst of writes, you write them into the journaling area, and then like you install the transactions later, right? And at this point, this can be kind of split into different methods, and like this is what the pretty good file systems are doing. There's still like, of course, if you're writing gigabytes, then you're still stuck with doing something when you will hit the bottleneck of a double write. But in most cases, it's acceptable. But again, for write heavy workloads, maybe it's not ideal. And so this is still an active area of research, making sure that file systems are fast enough and maybe can avoid this double write. Especially, it makes sense to do it for in-memory file systems, especially file systems. You say, look, what is the purpose of having a file system in memory? So you lose power, you reboot. Today, in practice, we have two other memories. We have a remote memory, which is attached to your machine, but it's really backed up different blade or by different server in a data center. And the fact that you lose power doesn't mean that your memory loses power. So it's persistent. And also we have non-volatile persistent memories, which are still people are still on split whether it's a good design choice to use them in a data center, but it's a DRAM-like memory, but it's persistent. So if you lose power, the data is there. You reboot and come back. And for those, like the overhead of those double writes is probably not ideal in most cases. It's just too expensive. Okay, the next layer is the inode layer. So inode layer sits right above the transactions, just because majority of the inode operations will trigger multiple writes. That's why we need a transactional layer underneath. Specifically, inodes are, as I was discussing before, they describe a single unnamed file, meaning that they talk about where the file is on disk, right? And so remember, inodes on disk, they sit in this inodes area. So each of this, it's just a giant array in x86. Each inode has a number. So like this is like number 17, and then it becomes inode number 17. And what you read from this array is this data structure, which has a couple of fields, but most importantly, it has a size, and it has the metadata for how to translate the logical addresses within the inode to actual physical addresses on disk, right? So for example, if you're trying to read, like if you say, look, I want to read block number 0 from the inode. In x86, inodes have 12 direct blocks. And essentially here, you just simply remember that when you're reading block number 0, it will be sitting in block number 77 on disk, right? When you're reading number 2, you go on. When you're reading number 12, or like specifically 11, you go to this one, which is like, I don't know, number 17, for example. But when you're past this first 12 direct blocks, and this is a compromise to make sure that you can access small files fast, you go to this indirect block, and the indirect block is kind of like a page table, points to the root of a data structure of the block. Essentially say, okay, my next level of translation is this indirect, is in the block 66 on disk, and it also has like 128 entries starting from 1 to 128 with pointers to other disk blocks. So, right? So for example, if you're trying to read block number 13, you will, or block number 12, if you start from 0, you will hit this translation, and then the block number 12 will be pointed by this pointer. Does it make sense? So I explained it before, so it's not super hard. So if I ask you a question, what is the maximum size of the file which x86 supports? One. So it's essentially the formula is you have 12 direct blocks and 128 indirect, right? And so that's the number. You multiply by 512, it's 71 kilobytes. So not large. And again, for educational purposes, it's fine. In our homework, we will exchange this data structure. That's why it's important to like kind of listen a little to make sure that we support infinite files. And specifically, we'll do it through a mechanism which allows us to, for example, instead of using 128, this will point to the next indirect block. And essentially you say, when you ran out of this first 120, in our case, it will be 127 blocks, you go and fetch the next level and traverse this linked list, right? It's a technique which was used in the, I think it was called FAT file system on Windows. It's, again, we're simplifying everything, but it's one way to support infinite files. Of course, it's not ideal because you have a linear scan, which is here, which, like, if you have a large file, you're traversing this linked list, and it's by far not the fastest mechanism. And alternative methods to implement those infinite files is to kind of like grow this part of the data structure and turn it into a tree. But again, just for simplicity, to simplify the homework, we'll just doing the linked list. Okay, cool. So like specifically, this is the definition of the inode on disk. x86 uses this D inode, D stands for disk. So it says most important fields are the 12 translations, this direct addresses, the size of the file, and this nlink. It's a number of times the inode, is referenced in a file system. So it supports reference counting. So essentially, when this counter drops to 0, then the inode is freed, goes back to the pool of free inodes. And that's why, remember, I think one way to implement a temporary file is to essentially create a increment, like make sure that this counter drops to 0 the moment you close the file, and this time like it disappears from the file system, and then everything essentially gets cleaned up because it's all reference counted. So again, x86 does this clever trick, and it caches inodes in memory because obviously you don't want to go to disk every time you access an inode. And so it has a kind of like a mirror representation of an inode in memory. So essentially most of the same fields. Here it just remembers some additional fields, which also like says, okay, this is how many times this inode is referenced in memory, and it will get deallocated in memory when this counter drops to 0. But other than that, the fields are the same. And the way x86 uses them, it implements a cache of inodes. So again, so kind of similar to a buffer cache, it says I have an array of inodes in memory, and log to make sure that we're synchronized. This is statically allocated. And then every time you try to allocate an inode, you essentially go like a typical life cycle. You say, look, I want to read an inode number from this specific disk. You use this iget function, and this iget function goes to the inode cache, and like it also implements just traversal as a link, like as a loop which traverses the array of inodes, figures out an unallocated number in that array, returns a pointer to this position in the array as an inode pointer. You acquire a log, you do some modifications to the inode to make sure that if the same inode is modified concurrently, because someone else can open the same inode with this iget function, and then you unlock it and then put it 0. And this iget implements the ref count, and this one decrements the ref count. And essentially, at some point when no one else is referencing inode in memory, it goes back to the free pool of inodes. So specifically, this iget function, what it does, it just similar to buffer cache, goes through the entire cache from 0 to the max number, trying to find the inode which matches the same device, same inode number. If it found it, it increments the reference, returns the pointer. If it didn't find anything, but it found the unallocated inode with the reference 0, it remembers the empty position, meaning that it will try to, how does it use empty here? It's a optimization to come back to this position again, but I don't exactly understand how to use it here. So forget about it. So it just sets the ref to 1, returns it to the user, right? And at this point, we're ready to read and write this inode. So essentially the file system, the way it's used by the file system. So for example, when you implement a sysread system call, when you invoke a sysread system call, remember that I say really inodes are referenced on files. So you get the file when the user passes a file descriptor number, you essentially convert it into a pointer to a file data structure. So the struct file. So do we remember how we do this conversion? Where this F comes from? A pointer to a file data structure. To this one. Anyone? So we have remember in a process data structure, we have an array, a file descriptor array, a file descriptor table. And this file descriptor table has pointers to those files. So essentially a pointer, like user passes an integer, like says 1, right? You get this with the arg fd, because you say argument 0, read it as a file descriptor. You go into this table and user, for example, passed 1, you check that it's valid, and this one will be pointing to a file, and this file will be pointing to an inode, right? I mentioned it last time because each file will have an offset which tracks position within the inode which you're currently reading. So let's take a look. So essentially, sysread uses this file read, passes f file data structure, but internally what happens is that it will have a pointer to an inode. So this is how we resolve, remember, arg, when you read an integer from the passed by the user code, meaning that user passes, like, for example, 3 in this example, 3 points to a file descriptor table points to a file data structure in a kernel, right? So you essentially get it from the file descriptor table, which is part of the process data structure. It's essentially cool. So this is the file descriptor table inside the process. So we get the pointer to a file internally gets the pointer to an inode. Let's take a look how it works. So if you have a file data structure, we can have a file of different types, and this is how the operating system implement this polymorphism. So specifically in x86, it can either be a pointer to an inode, or it can be a pointer to a pipe. That's why you can either read, like with the same API, sysread or sysopen, syswrite, you can open, close, and write. You cannot open the pipes, but you can create pipes and then read and write them. But essentially, the way it's implemented, that the file itself tracks the type. So it's either a pipe or an inode, and essentially it can be either readable or writable. And like when you open a file, you pass a flag saying, okay, I'm opening the file for writing or only for reading. And here you have either a pointer to an inode or a pointer to a pipe, and an offset within a file is tracked with this offset data structure, right? So essentially, remember, like same API allows us to read from a pipe as well as from the inode. But if it's the way the implementation of this file read function is like this. So you say, look, if I'm allowed to read a file, if I'm not allowed, like returning -1 as an error. If reads are allowed, I check whether it's a pipe or an inode, and if it's a pipe, the operating system uses this pipe read function. So essentially it goes into a pipe and reads some data from a pipe. If it's an inode, at this point, you say, like, I will log the inode. I'm making sure that no one else can modify it for now. And I'm trying to read from this inode at address, like into the buffer pointed by this addr variable, from the offset pointed by the offset field of the file, and bytes, right? So essentially, at this point, there are no names, right? So it's unnamed file. You already opened it through some name. You have a pointer to an inode. You keep reading inode with this read I API. And we saw this read I, and you're using it right now in your homework when you're reading the L file, right? So you use this name I API to convert from a name to an inode. We'll cover it later, but right now you're using this read I API to read an inode. And this is kind of the core API, which allows us to read something from a file, right? So what happens internally is the following. So inside the read I, you perform a couple of checks, because this API is reachable from user level. User may try to confuse the kernel, trigger an attack. So specifically, you check for whether the offset within the file is greater than the size of the inode, because you don't want to try to read past the max size. And right now you have a log, so nothing will change, right? So inode is not changing because you locked it. You also check that the entire read will be within the file. So meaning that the offset plus n is within the file, right? And my question for you is, what is this check for? Because supposedly you just have to, like, if this is the file, or pardon, I should say inode, and you're trying to read from an offset, and you're trying to read n bytes, you just have to verify that the entire read is within the file, right? But then you still use this check. What is this for? Correct. So again, this is this kind of a crazy domain of operating systems, or anything today which is like external facing, which can be exploited. So the user can carefully craft this read in such a manner that this offset plus n, which are both signed integers, right, can overflow. And so you will pass this check because it will be smaller than inode plus size, but then internally, like, you still will try read past the inode size. So this is kind of, yeah, this is crazy. You always have to check for those overflows. Does it make sense? So, and again, so this is how attackers kind of like, in Linux, we have today roughly 27 million lines of code. It's a lot of code, right? So right now, x86 is roughly at, I think it's 9,000 lines or maybe 10. It's just thousands. Like add 3 more zeros and multiply by what? By 3 again, right? So Linux is giant. Imagine how many of those bugs are there, like, and it's developed by people like you. And you always, like, every line you add to the kernel, not all, but a lot of lines have to do checks similar to these ones. Okay, so we have to be careful. Anyway, but if I ask you a question, what's the logic of this read-I? So how can we build it? What's the implementation? It's on the screen, but like, let's just quickly hypothesize. And because implementation, like, conceptually is very, very simple, right? But the devil is in the details a little. So how do we read an inode? What needs to happen? What is an inode? Do you remember? Inode is this thing. How to read, have some offset, right? You want to read from this offset some number of bytes. Let's read just 1 byte, for example. Correct. So essentially, I cannot say that we read a size first, but essentially you say, look, if the offset falls, let's say, into the middle of this block, right? You have to read the block, like, and you have to do the translation by using this logic of this 12 direct blocks and then an indirect translation, right? And do it in a loop, right? And for every time you try to read something, you do this translation, right? And so this is the logic of this function which implements it. The reason I'm again spending time is because I want you to modify those functions to make sure that you kind of go through them in your homework. You don't have to modify read-I because read-I will stay the same, but you will have to modify the function which implements the translation because we're changing the way we will be translating, right? So here, what happens is that we just run a loop. What we do here, we say we want to read a total number of bytes, right? From 0 to less than n. And we're starting from an offset, and we'll be reading them in a loop, right? And essentially, there's like a bunch of kind of like boundary conditions. You have to round up the things correctly and stuff like that. But the most interesting part of this is this bmap function. So it stands for block map. So this bmap function performs the translation. So it takes a logical address, like essentially it offset divided by block size, because it reads in terms of blocks, but really it just takes an address. Offset is an address. logical address within the inode and then translates it into a physical address on disk, it returns it and puts it as an argument into the bread, right? Because bread just reads physical blocks from disk, right? It doesn't know anything about the inodes. So the output of this function is a block number. And so what we're doing internally, we do this translation, right? So bmap internally will implement the logic of saying, okay, am I reading the block which falls in the first 12 direct blocks? Then just immediately return the whatever, read the number saved here and return it to the bread function. If, however, it's larger than 12, read this number, figure out the block which contains indirect translations, and then, like, of course, subtract 12 and read the number from here, get the pointer to the block on disk, right? And return this number, right, to the bread function. And the bread will go ahead and will read this block into the buffer cache. Make sense? So again, conceptually not very hard. So it's kind of like walking a page table, but in software, because there is no hardware to implement the logic of this bmap, right? And each file system implements its own mapping, and they can get complicated, optimized for different use case scenarios. But let's take a look at this bmap function. So essentially, this bmap is important because this is what you will be modifying in your homework assignment, right? So again, conceptually, everything is very, very simple. You say, I got the block number as input. And you say, look, if bn block number is less than the number of direct blocks which I support, just simply read this from the array of direct address translations. If it's suddenly 0, like it was never allocated, because bmap works for both reads and writes, and maybe you never yet had this block, so it's a brand empty file and you're reading block number 0, so it will allocate it. It will go to like block allocator, which we'll cover in a second, returns a block number and updates it into the, like, writes it back into this array. It's kind of like allocating an intermediate page in a page table. Although here we're just allocating a block and we're returning the address directly back to the user, right? If we, however, reach this line 5170, it means that it's not a direct, it's larger than a number of direct blocks. We subtract this number saying, okay, like, sure, let's keep translating. We have to read the indirect block. We do a check here because we say that we only support the maximum file size. So we do this check, making sure that the user, and again, at this point, this is kind of the questions you keep asking yourself when you're building an operating system. Remember, we already did those checks for the size and an offset in a previous, and for the overflow, and yet we never checked for the maximum file size, right? So probably this is a good spot to say, look, if you're trying to, you are writing, everything was like totally legit, and suddenly you reach the max size of a file. And at this point, you will have to return an error, right? So, okay, sure, bmap says, okay, we pass this check. At this point, you figure out the position of this indirect block on disk. So specifically, let me erase everything on this slide. Like position of this block on disk, right? Because you already subtracted 12. Again, it may happen that it was never allocated because it's the first time you're touching it. Then you go to the disk allocator, to the block allocator, get this address, put it back in exactly this slot, right? To make sure that you establish this link. If this link already exists, you just simply read it from disk, right? But you have to read it first because you don't know what this, like, you don't have it handy. So you literally read this block into the buffer cache. And then it cached in the buffer cache. And at this point, you say, look, it's all good. So I have a pointer to the data. You typecast it into an array of unsigned integers because that's your translation. All of it is just, these guys are unsigned ints, you int. So you're just, for simplicity, you typecast it and use it as an array. And at this point, you say, look, I will try to get an entry in, number BM because you already subtracted 12 here. So it's a legit entry. You get the address. If it's 0, it was never allocated. Then you may allocate it again. And you put it back into this, like you make an association in this array, making sure that if this one was never allocated, you put association, making sure that this gets written to disk. But of course, you first modifying just memory, right? So nothing touches disk here. And this is one example where you're using this log write API, making sure that you never lose this address. So it's part of the transaction, right? So this bmap API will never be used as directly, because if you immediately update an inode, but you really never completed a write, you're probably in a bad state. And so essentially, and then you release the block which you were accessing, which you read here, right? So essentially, your goal in a homework will be to modify the logic of this translation, making sure that it can traverse the linked list instead of like just accessing one layer of interaction, which is this one, right? But you will be trying to like say, okay, I will check if my block falls here. If not, I will traverse further until it will get to the next block of indirect addresses. Make sense? Okay, again, not very hard, but just makes sense to go through this code at least once to understand how it works. Here I have like some explanations on the slide, so you can read them later, making sure that you understand how it works. But more or less, this is kind of the logic of this inode layer. Bmap function, inode cache is there, but other than that, we've more or less covered it. So any questions about inodes? All good? Then one tiny piece, I don't want to spend a lot of time on it because it's a layer of a block allocation. As I said, the block allocator is just a bitmap. And we've seen how this API is used. It uses these two functions, balloc, block alloc, and block free. So kind of implementation is low level. You have to like carefully traverse. You're reading the block, then you're going into the bytes, but really you have to reason about the bits. So there will be a lot of this like low level bit manipulating operations, but conceptually it's just a linear scan of the block allocator. Obviously, it's not ideal because it makes everything quite slow, because like as the file system is getting more and more, is getting full, any write will invoke this bmap, right, on the critical path. And bmap will be using these block alloc operations. And these block allocs, each of these will be traversing the bitmap, right? So essentially, as the file system gets more and more full, everything gets slower and slower. And it's kind of like, of course, a design flow. Back in the days, we were asking people to fix it, to essentially implement an optimization, which will allow you to somehow implement a faster block allocator. And we talked about it a little bit. So, but what kind of optimizations are possible here? Like, what is the simplest? Like, you really, this is just a bitmap. It's on disk, but it's a bitmap. What can we do to make it faster? Individual bits. Yeah. Why not? Right, because you used to the fact that you can create free lists in memory, but obviously, why not to create a free list? And specifically, the way we can do it is that we say, look, since pointers themselves probably are 4 bytes, so instead of like having each of those guys be a pointer, because we really track bits, right? So we can say, look, we will be tracking pointers to like maybe we will split this area into like 3 different categories, kind of like empty, meaning on this list, everything is like really all these bits are untouched, all the free, partially allocated, and some bits here are taken some not, and a full list essentially like everything is allocated. And then like essentially manage those lists. And if you try to allocate something, you go to a partially allocated and you say, look, you only scan so many bits now because this array is smaller, and you immediately hit, you pick one. When this block becomes completely full, you take it off this list and put it in a list of full blocks, right? And just go to the next one. And if it becomes free, then you put it in the list of free blocks, right? And it's one implementation. So, but you can come up with a different one, but that's one. It's a little advanced, and this way we'll talk about it. This is how the memory allocator work as well. But is there like an even simpler optimization which is less efficient than like clean tracking of everything as collection of lists, but still effective as a means to solve the current problem of linear scan from the beginning until the first unallocated bit? Kind of like a straightforward dummy, but yeah. So what you're suggesting, you say, look, let's also maintain a pointer to the first empty element, right? And so at least you may try to scan not from the beginning, but for this empty, and just go forward from it. Of course, it works only so well when this bitmap is not fragmented. It's fine when it's fragmented, and then it becomes like less efficient because you might still be doing long scans, right? So but this empty is a fix which we're suggesting in a homework because it's very simple, right? But at least practical. But a real fix would be something like maintaining those linked lists explicitly to make sure that we could keep track of bitmaps. Okay, so I don't want to spend more time on a local allocator. So conceptually simple. One interesting layer which worth discussing is this directory layer. It's essentially the layer which provides human readable names. And in its file system, a directory is just an inode. And an inode is essentially like it's implemented as the directory is implemented as this data structure. You have an inode number and a name of a file or the next inode, right? So it's kind of like you store this table. This is the inode number, and this is a name, kind of like home, right? And directory is just an inode, so it can be read, right? And it can be linked from here to the next level. So, and this is how you traverse from one directory to another because it's just inodes, right? And so what you do here is that you implement this inode will have a special type directory, so to distinguish it from regular files, which are not directories. And you have a couple of functions which allow you to kind of do a lookup, right? And the most powerful function in this family is this namei function, which we mentioned a couple of times. So namei takes kind of a recursive pos /user/bin/shell and resolves it. So essentially just what it does, it just will parse the string, split it into like root, then inside the root it will find user, inside user it will find bin, and inside bin it will find a pointer to an inode which represents the shell, right? And again, conceptually, if you think about it, building this function is not super hard. So what it does is that you say, look, I will take a string and I will just parse it. And that's essentially what happens. So when you say you issue as open system call, internally it's implemented with this sysopen. And what it does, like it starts a transaction. That's one example again, like because remember, okay, good question. Why do we have a needed transaction here? what can get written underneath? It's a good kind of exam level question. Because supposedly you just want to open a directory, right? Will it trigger any writes? Which ones? No. I mean, yes and no, but be more specific. Which metadata? Last opened? This way. Yeah, that's a good guess. I'm not sure x86 does it. Maybe I agree with you. So what you're saying is that every time we open a file, we might update an inode. If I remember correctly, it doesn't, like, if we look at the definition of the inode data structure on disk, I don't think there is a metadata maintained. So this is the entire thing. So there is nothing about time. But in a real file system, yes, you most likely maintain metadata about last access time, right? Good guess. What else can go wrong? What else can trigger a write? More kind of like less esoteric. So very, very straightforward. Anyone? No. How do you create new files? You open them, right? So, and like again, the exercise here, I mean, I get it. So it's a little mundane and we like talk about all these layers. They show a lot of source code. It's hard to keep track of what's going on, but in the end, like if you really want to learn it, you will have to like at least read through this source code and then use my recorded lecture as a guide, maybe to simplify it. But the idea here is that to like kind of like look through those layers and make sure that we understand what's going on. So here, when we open a new file, right? So we will essentially traverse. We will traverse the layers of those directories, maybe moving from like from maybe if it's a root directory, we move to something like user, to another inode which implements a user directory. This is user. Inside user, we find something like, I don't know, home or something. I don't know where a user is. We traverse further, and inside maybe home, we try to add a file foobar. And like you essentially saying, okay, this will trigger a write into this directory and specifically in the block which contains this directory. And my explanation might not be, first of all, I can be wrong. That's my guess. Second, maybe something else can trigger a write as well. So you really have to like carefully look through those and understand what's going on. But essentially, what I wanted to explain that name_i, like if you look at the implementation of name_i, it will be splitting the string and traversing the layer of like the hierarchy of directories until it reaches the final leaf in this hierarchy, which is like in my example, maybe this foobar, and this is the inode which represents the foobar, and this is the pointer to this inode which gets returned. Make sense? And again, so the high level story here is that we understand how directories work, right? Okay, so we talked about the file descriptor layer. We kind of understand that file descriptor is just a collection of like inside the process data structure. It's just like if we have a proc, inside the proc we have an array. User passes a number, like number 1. This has a pointer to a file. File has an offset, has a pointer to an inode potentially, right? And inode is this has enough information to translate where the files are on disk, right? And those blocks, they essentially can be anywhere on disk here, right? Although like this file logically is continuous, so essentially number 1, 0, and so on, right? And another just kind of like overarching final comment is that you never access those blocks directly. You have a bcache layer, which essentially brings those to memory, right? And essentially, the way you access those guys is you have something like a block and a data pointer, and this is where it points to the actual location in memory. And moreover, you never really reach like layers above the buffer cache or above the logging layer, never really write directly to disk, but essentially everything is first written into the logging area from the buffer cache. You first write here, and then you install those writes back here. And this kind of picture kind of captures everything what we discussed. So I kind of argue, okay, we understand now how file systems work. And so that was my last slide. I cut a couple just to make sure that we are not overloaded and we can finish on time. Any questions about the file systems? Okay, cool. So at least you understand how it works. You know, like when someone asks you what is an inode number, each file will have an inode. Inodes will have numbers. Inode numbers will be unique, stuff like that. So if someone asks you those things at the job interviews, you can like quickly, if you have a slide deck, quickly figure it out by looking at those slides. Okay, and so I will stop here, and then next week it will be actually last week of teaching, right? If I remember correctly, and there will be a 1 day of recap. So next week we will cover synchronization, kind of how x86 boots multiple CPUs and what it means to synchronize access between multiple processes and execution on multiple CPUs.